Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Perpendicular Transport in Single and Multiple Heterostructures from the paper Physics at Nanoscale. So the learning objectives of this module are that first we will be discussing the perpendicular transport in single heterostructures. Secondly, we will be discussing the perpendicular transport in multiple heterostructures. So students, let us start with the basic introduction about the module. For transport through the heterostructures, there are two situations: when the carrier energy is greater than or less than the conduction band minimum within the barrier region. When the electron has energy greater than the potential barrier, it simply moves from one region into the other with no chance of reflection. However, if the electron energy is less than the potential barrier in the second region, the electron is reflected from the barrier back into the same layer. But this situation is different when the problem is treated quantum mechanically. So, if the problem is treated classically, that is when electrons suffers no reflection at the hetero interface, with this assumption, it is relatively straightforward to calculate the final electron state after crossing the interface. So the electron energy should be conserved upon crossing the hetero barrier. The electron transmission at a potential energy step can be obtained quantitatively. So this figure shows a heterostructure system with a band offset of delta EC, that is the difference between the energy levels E1 and E2. The energy of the carriers in the left side, that is wide bandgap semiconductor, and the right side, narrow bandgap semiconductor of the heterostructure, are E1 and E2 respectively. Now assuming the parabolic energy bands, the conservation of energy requirement demands that E2 must be equal to E1 plus delta EC, that is h cut square K2 square by 2m2 must be equal to h cut square K square by 2m1 plus delta EC, where K1 and K2 are the K vectors and M1 and M2 are the effective masses of the carriers in the narrow and wide bandgap semiconductor layers respectively. If the z direction is the direction perpendicular to the heterostructure, conservation of linear momentum leads to K1x equal to K2x, K1y equal to K2y. Let us assume that the electron is confined completely to the xz plane. So now using these equations, we get h cut square by 2m1 multiplied by bracket k1x the square plus k1z the square bracket close plus delta EC equal to h cut square by 2m2 plus multiplied by the bracket k1x square plus K2Z square, bracket close. So if the energy of the incident carriers is known, then K2Z is given by K2Z the square is equal to bracket M2 by M1 multiplied by K1X square plus K1Z square, bracket close, minus K1X the square, bracket close, plus 2M2 delta EC by H cut square. Hence, the final state of the electron in the narrow gap semiconductor layer is given by E2 is equal to E1 plus delta EC and K2X equal to K1X. Then K2Z will be equal to the square root of square bracket M2 by M1 bracket K1X square plus K1Z square, bracket close, minus K1X square, square bracket close, plus 2MT delta EC by I square. So this formulation applies if electrons are treated classically and is important in those cases where the carriers traverses a single potential barrier and reflective losses at the barrier is negligible. However, an electron is a quantum particle, so there is some probability that the electron will be reflected as well as transmitted. Whether the electron is incident from the wide gap semiconductor into the narrow gap semiconductor or vice versa, there is a non-zero probability that it will undergo reflection at the hetero interface. It can be shown that when the mass is different between the two semiconductor layers, the transmission and reflection coefficients can be given by capital T equal to 4 multiplied by K2Z by K1Z multiplied by M1 by M2 divided by 1 plus K2Z by K1Z multiplied by M1 by M2 the whole square, and capital R is equal to 1 minus K2Z by K1Z multiplied by M1 by M2 the whole square divided by 1 plus K2Z by K1Z multiplied by M1 by M2 the whole square. So the T and R in these equations corresponds to the transmission and reflection coefficients for the particle flux at the hetero interface respectively. In the case where the electron is incident from the narrow gap layer into the wide gap layer, so that the energy of electrons is less than the potential barrier height formed by the wide gap semiconductor material, classically the electron would be reflected at the interface, but the transmission of electrons into the other side of the potential barrier would be zero. However, quantum mechanically, there would be always a non-zero probability of the transmission of electrons into the other side of the barrier, even when its energy is less than the barrier height due to the phenomena known as tunneling. So when the energy of the electrons is less than the potential barrier height, the transmission and reflection coefficients are given by capital T is equal to 1 plus V naught square sine hyperbolic square of sine h square k to b divided by 4e V naught minus e to the power minus 1. R is equal to 1 plus 4e V naught minus e divided by V naught square sine h square k to b to the power minus 1. So it is clear from above expressions that there is a non-zero probability of the electron being transmitted through the barrier when its energy is less than the barrier height. An interesting condition occurs when two barriers are used to enclose a small potential well known as quantum well. So when the energy of the electrons matches with the one of the quantized energy level in a quantum well, the transmission coefficient approaches unity. This effect is known as resonant tunneling. So students, let us now discuss the resonant tunneling in quantum wells. An interesting condition occurs when the two barriers which are used to enclose a small potential well known as a quantum well, as discussed before, when the energy of the electron matches with one of the quantized energy level in a quantum well, the transmission coefficient approaches unity. So this effect is known as resonant tunneling. So resonant tunneling provides direct evidence for the existence of bound states in quantum wells. So the total energy E and the momentum parallel to the interface or perpendicular to the layering direction, they are conserved in the tunneling process. Since the potential acts only in a certain direction, that is a z direction, the one-dimensional Schrodinger equation becomes minus h cut square by 2m multiplied by d square by dz square plus vz minus e multiplied by psi e equal to 0. So continuing our discussion on resonant tunneling in quantum wells, psi e as a function of z1 minus equal to psi e as a function of z1 plus, that is 1 by m1 d by dz psi e at z1 minus equal to 1 by m2 d by dz of psi e at z1 plus. So the current density for tunneling through a barrier becomes Jz is equal to E by 4 pi cube, basically h cut, multiplied by integral over dkz d square k perpendicular fe tez multiplied by de by dkz. So these are the figures which shows a rectangular potential model where the part A, which is used to describe the effect of an insulator 2 between the two metals 1 and 3. So when a negative bias is applied to one, electrons with energies up to the Fermi level EF can tunnel through the barrier. For small voltages, the barrier becomes trapezoidal, but at high bias, that is in the last figure, it becomes triangular. Now, if an external bias V is applied to the barrier, the net current flowing through it is the difference between the current from left to right and that from right to left. So Jz is equal to E by 4 pi cube h cut multiplied by integral over dEz d square k perpendicular square bracket Fe minus Fe plus Ev square bracket close multiplied by Tez. So dkx dky equal to d square k perpendicular equal to 2m by h cut square de perpendicular, where E perpendicular equal to h cut square k square perpendicular by 2m. So Jz is equal to Em by 2 pi square h cut cube square bracket Ev multiplied by 0 to Ef minus Ev over dEz t as a function of Ez plus the integral from Ef minus Ev to Ef over dEz multiplied by Ef minus Ez multiplied by t as a function of Ez square bracket close. Now this is applicable if Ev is less than equal to Ef. Now if Ev is greater than equal to Ef, then Jz is equal to Em by 2 pi square h cut cube multiplied by integral from 0 to Ef over dEz multiplied by Ef minus Ez multiplied by Tez, which can be evaluated as long as the tunneling probability through the barrier is known. The Schrödinger equation for a heterostructure in the case where energy exceeds the potential barrier can be solved for the incident, transmitted and reflected electron wave functions as psi I is equal to A multiplied by exponential iota multiplied by kix plus kiy, psi t is equal to B multiplied by exponential iota multiplied by ktx plus kty, psi r is equal to A multiplied by exponential iota krx plus kry respectively, where capital A, B and C are the amplitudes and x is the direction of propagation. So the continuity of the wave function across the hetero interface implies that psi I 0y plus psi r 0y equal to psi t 0y. Since the y components of each k vector are equal, that is kiy is equal to k1y equal to kry. So the above equation implies that A plus C must be equal to B, or we can say the I plus R should be equal to T, where R is C by A is the reflectivity and T is B by A is the transmissivity. So the probability current density normal to the interface Jx is conserved, which yields Jix plus Jrx equal to Jtx. Now continuing our discussion, here Jix is equal to 1 by, that is I by M1 multiplied by A star Kix, Jtx equal to I by M2 B star Ktx, Jrx equal to I by M1 C star Krx. Now substituting these equations in the equation of A plus C equal to B, or I plus R equal to T, and recognizing that KRX must be equal to KIX, it yields M1 KTX by KIX M2 multiplied by T square plus R square equal to 1. Now combining this equation and the equation A plus C equal to B or I plus R equal to T, the electron amplitude transmissivity becomes T equal to 2 M2 by KTX divided by M2 by KTX plus M1 by KIX, and the electron reflectivity is given by R is equal to M2 by KTX minus M1 by KIX divided by M2 by KTX minus M1 by KIX. Now recognizing that KIX is equal to KI cos theta I and KTX is equal to KT cos theta T. Now putting all these values, the transmission and reflection amplitudes are T is equal to 2 root of E by M1 cos theta I plus root of E by M1 cos theta I plus root of E minus V by M2 cos theta T, and R is equal to root of E by M1 cos theta I minus root of E minus V by M2 cos theta T divided by root of E by M1 cos theta I plus root of E minus V by M2 cos theta T. Resonant tunneling diodes. Diode is nothing but a two-terminal electrical device. They are the simplest of the active elements of electronic circuits. Diodes shows non-linear current voltage characteristics. The double barrier resonant tunneling diode is a nanoscale quantum diode. Consider a double barrier heterostructure. Now a quantum well is prepared by embedding a gallium arsenide layer in between the two aluminium gallium arsenide layers with or without the spacer layer. Inside the well, several quantized energy levels can exist. So, this implies that the quasi-bound states, that is, which have the finite probability for the electron to tunnel out of the well. So, the resonant tunneling diode can be thought of as the system with two contacts, that is with 3D electron states and a quantum well with 2D electron states. As shown in this figure, the three subsystems, they are weakly bounded. Now these are the figures. The first figure A shows the probability of tunneling through a double rectangular barrier as a function of energy. The carrier mass is taken to be 0.1 ME in the barrier and 0.067 ME outside, and the width of the quantum well is 60 angstrom. Now the part B, that is the figure B, shows the tunneling probability through a double barrier structure subjected to an electric field of 105 volt per centimeter. The width of the left barrier is 50 angstrom, while that of the right barrier is varied between 50 angstrom and 100 angstrom. So here, as you can see, the peak at 0.16 electron volt corresponds to the resonant tunneling through the first excited state of quantum well. Perpendicular transport in multiple heterostructures. Using the result above, one can now determine the transmission coefficient for a multi-quantum well stack under the condition that the incident electron energy is greater than the potential barrier height. So if there are a system of M layers comprising of a multi-quantum well structure, the solution can be obtained by solving the Schrödinger equation in each layer and matching the appropriate boundary condition at the interface. So the general expression for the probability amplitudes for the M layer in terms of the M plus 1th layer is given by the matrix psi im and psi rm equal to 1 by Tm multiplied by the 2 cross 2 matrix having elements 1 Rm, Rm1 multiplied by the 2 cross 2 matrix, that is exponential iota Km dm cos theta m 0, 0 exponential minus iota Km dm cos theta m, where Tm and Rm are the amplitude, transmissivity and reflectivity at the M-1 and M interfaces. Km is the magnitude of the electron wave vector in the layer M, dm is the thickness of the layer M, and theta m is the angle of the wave vector direction in the layer M. So, for the entire stack of M layers, the total normalized transmitted electron wave amplitude psi t m plus 1, the final region is m plus 1 after the mth stack, and the total normalized reflected electron wave amplitude psi r r0 in region 0 are obtained through chain multiplication of the total m plus 1 versions. The resultant expression is the matrix 1 psi r0 is equal to the product from m equal to 1 to capital M multiplied by 1 by Tm multiplied by a 2 cross 2 matrix 1 Rm Rm1 multiplied by again a 2 cross 2 matrix exponential iota Km dm cos theta m 0 0 exponential minus iota Km dm cos theta m multiplied by 1 by Tm plus 1 multiplied by 2 cross 2 matrix 1 by 1 Rm plus 1 Rm plus 1 1 multiplied by psi Tm plus 1 0. So this can be solved directly for amplitude, transmissivity and reflectivity. So using this equation, T is possible to calculate what the transmissivity of an electron at an arbitrary angle of incidence is on a multi-quantum well stack under the condition that the electron energy exceeds the potential barrier height. So one can design the multi-layered heterostructure stacks, often referred as the superlattice, such that the transmissivity can be maximized for certain electron energies. So students, let us summarize what we have learnt in this module. First, we discussed about the tunneling, which signifies that there would be always a non-zero probability of the transmission of electrons into the other side of the barrier even when its energy is less than the barrier height. Secondly, we evaluated the incident, transmitted and reflected electron wave functions, which can be solved using Schrödinger equation for a heterostructure in the case where the energy exceeds the potential barrier. Then we discussed or evaluated the transmissivity of an electron at an arbitrary angle of incidence or multi-quantum well stack under the condition that the electron energy exceeds the potential barrier height. Thank you.